Today we are going to be looking at thermal expansion. Thermal expansion. That is the increase bodies do undergoes if they are subjected to change in temperature. Now, expansion means increase in the size of a body. If you have a note, you can jot it down, it's no problem. If I call questions out, I'll dictate it to you guys and you can jot it down. I will put solution to them here. Now, expansion means increase in size of a body. When a body increases in size. While thermal expansion is the increase in size of a body due to temperature change. Due to what? Temperature change. Now, and we have different applications of this expansion. We're not going to that place now. What I'm actually looking at in this class are the forms of this expansion. We are talking about this thermal expansion. We are talking about the forms of them. We have mainly three forms of thermal expansion. We have what we call the linear expansion. We have what we call the area expansion, which can also be called superficial expansion. That's the second one. Then we have what we call cubic or volume expansion. That's the third one. Now, in this class, we are going to be looking at mainly the linear expansion. And what you can show the body is linear expansivity. Actually, linear expansivity is coming from linear expansion. Now, what is actually linear expansion? What is linear expansivity? Now, before we go into that definition, there's something you're going to do for me now. Ensure you have subscribed to this channel. It's very important. This channel is highly educative and all science students need it. As far as you're a student, you're a physics student, you're a chemistry student, you're a mathematics student, you need this channel. And share it to others, share the link to others, let them subscribe. It's very important. And subscription is free. It's very easy to do. What you have to do is just to if you know you are registered with YouTube, you just register with a valid email. It's just like you are registering for all these other social media, but this one is so it's basically for education. It's basically for education. If you check our description, our channel is basically for education, which is for mathematics, physics, and chemistry. And today we are looking at expansion in physics. So please ensure you have subscribed. Then after that, ensure you don't skip any part of this video. And don't ever try to skip what we are saying. Don't skip what we are saying. Don't say that these words are not what I'm looking for. Everything is important. Everything is important. All the information you are gathering is important. And lastly, please try and share the videos to others. Just share the link of the videos to others. And it will be very helpful. So please, if you have a comment, just comment us in the comment section after this class. So let's go back to our linear expansion. Now, linear expansion means when a body increase in its length. If a body is increasing in length, we call that kind of increase linear expansion. We call it linear what? Expansion. Now, what about linear expansivity? Linear expansivity is the change in length per unit length to degree rise or per degree rise in temperature. When a body increases in length over the original length times the temperature increase, we call it linear. Actually, they call it the coefficient of linear expansivity. Look at it here. This alpha is equal to the increase in length per unit length per degree rise in temperature. Now, this change in length, that's the L, is called change in length. That's what we call it. And it's set here as L2 minus L1. Now, what is L2? What is L1? L2 is called final length. L1 is called original length. And this change in theta is set here as theta 2 minus theta 1. Set here as theta 2 minus what? Theta 1. And we can as well look, they can as well ask you to look for. Now, look at what you can be asked to look for here. Number one, you can ask to look for this expansion or change in length. You can ask to look for the original length of the material. You can be asked to look for the increase in temperature or change in temperature. You can be asked to look for linear expansivity. You can be asked to look for the final temperature, original temperature, the final length or original length. Those are the questions you'll be expecting from this part of physics, in this linear expansivity. Now, assume we were asked to look for our final length. You can just make L2 formula here and look for it. But what if I of linear expansivity. In terms of this linear expansivity, and this is a symbol we call alpha. We call that alpha. And this expansivity represents linear expansivity. No, we cannot say, okay, the first thing we can actually say alpha is equals to L2 minus L1 because the L is equal as L2 minus L1 over L2 change in theta. So our L2 minus L1, L2 minus L1 will be equal to this times this because of the line alpha L2, like after L1, this is L1, alpha L1 change in theta. So in the same way, we can see that the L is equals to alpha L1 change theta. It's still possible to say that. So we'll see that. Now, the next thing is that our L2 will be equal to move L1 to this side, moving L1 to this other side. If minus goes to this side, we change to plus L1, then plus alpha L1 change in theta. So the next thing our L2 will be to factor out L1 since L1 is common to both sides. Then if you factor out L1, there's a coefficient to this L1 that is 1. Not this subscript 1, no. There's a coefficient to a number, any number that don't have any coefficients, or a variable that don't have any coefficients, whose coefficient is not stated, like x, y, z, and all that don't have any coefficient at the back, they are assumed to have 1 as their coefficient. So we have the 1 for this coefficient, we put it there, plus alpha change in theta. Now this will be the relation to calculate our L2 in terms of linear expansivity. You can also ask to look for this L1. In that place, L1 will be equal to, our L1 will be equal to L2 over 1 plus alpha change in theta. Our L1 can also be equal to that. L1 can be equal to that. Now, let's say we have a question. Let's assume we have a question. Let's say question 1. Let's say we have a question. Now, I'm going to say the question to you guys, then you write it down. Just write it down, go very slow by repeating it. Now, let's say, obtain the linear expansivity of a material. Obtain the linear expansivity of a material whose initial or original length was found to be 53.0 cm. Whose initial or original length was found to be 53.0 cm and expand 0.13 cm and expand 0.13 cm and expand 0.13 cm when the temperature was raised from 30 degrees Celsius to 70 degrees Celsius. When the temperature was raised from 30 degrees Celsius to 70 degrees Celsius. Now, what would be the linear expansivity? This material, the initial length was 53.0. So our original length, L1, is 53.0. And the guy expands to the expansion means change in length. In linear expansivity, expansion means the change in length was now 0.13 cm. When the temperature was raised from, now the first temperature is our 30, that is our theta 1, that is the first temperature there. Now move to theta 2, which is what? 70 degrees Celsius. 70 degrees Celsius. So our linear expansivity now can be our change in length over original length times change temperature. Change temperature is theta 2 minus theta 1. Our change temperature is what? Theta 2 minus what? Minus theta 1. So what do we do next? The next thing we are going to do here is to substitute this value to this formula. But look at we have cm, we have cm. And this one is degree Celsius. So temperature is a fundamental quantity. So that may not actually alter this unit. So what do we do here? You can convert both metric unit to meters by dividing this and this by 100. If you divide both sides with 100, you have the equivalent original length and expansion or change in length in meters. But if both of them are the same thing and are resolving linear expansivity, as long as the units are the same. Even though you don't convert to meters, you still get the exact answer. So I'm not going to convert anything since both of them are the same thing. So I'm just going to come to this place. I'm putting my expansion here over. Then our L1 is 53. If you do it this way now, this one is CM, the CM will cancel out. That's how we do it. So times, and our change temperature is 70 minus 30. So we're going to be having our 0.13 over 53 times 40. That will give us, if you use your cash calculator to resolve that, any calculator, you'll be having 6.1 times, we're going to be having 6.1 times 10 raised to power minus 5 per degree Celsius. That's what we're going to be having. 6.1 times 10 raised to power minus 5 10 degree Celsius. So that is our first question. Now let's have another question, question 2. Let's be fast a bit, long time. Let's do question 2 now. Question 2, number 2. Number 2, I say linear expansivity. And number 2 is to obtain the final length of the material. Obtain the final length, that is L2. Obtain the final length of the material. Obtain the final length of the material whose initial length was found to be, whose initial or original length was found to be 30. cm. Whose initial length or original length was found to be 30 cm. When the temperature increased from 20 degrees Celsius to 500 degrees Celsius. So the temperature increased from this to this now. What will be the final length of this one? So that's what I'm trying to say. Obtain the final length of that whose original length was this. If the temperature was what? Increased from 20 to 520 degrees Celsius. So I hope you understand that question. Obtain the final length of the material. Obtain the final length of the material whose initial length was this. If the temperature was increased from 20 to 520 degrees Celsius. Now, if the temperature is different from here to here, what will be the final length of this material? So you bracket it right. Take alpha to be equal to 1.9 times 10 to the power minus 5 per degree Celsius. In bracket it right. Take alpha as 1.9 times 10 to the power minus 5 per degree Celsius. So what they are asking for in this case now is the final length of this material. Is to look for the final length of this material. Remember we said solution. So the final length is equal to original length times 1 plus alpha change theta. Remember that? So if this one is cm and this unit was not given, no problem. After we have calculated it to get our answer, we can put our answer in cm. So just substitute. We have 30 times 1 plus 1.9 times 10 to the power minus 5 times 520 minus 20. Our change is theta. Our change in theta is theta 2 minus theta 1, which is 520 minus 20. That gives us 500 degrees Celsius. So times 500 degrees Celsius. So do this very well. Look at what I'm going to do for me here. You are going to do this way. 1.9 minus 5 times 500. Write it down. Then add 1 to it and multiply it by 30. If you do that with your cash calculator, it is multiplication of 34 addition using board mass. So if you do that with your cash calculator, your L2 will be equal to 30.285 centimeters. That will be your final length. That will be your final length of the material. Now, I can also ask you a question from this place. I can also ask you a question from this place. I can also ask you, what is the change in length of this material? Or what is the expansion experienced? Let's say question B, for this number 2 now, question 2B. What is the expansion experienced by this material? What is the expansion? Okay, let's do it this way. Let's do it this way. So that we still be in order. Now, let's say from question 2 below or question 2A. From the question 2 above, question 2A now, from this question 2 above, what will be the expansion experience? Expansion means change in length. Remember that? Expansion means change in length. What will be the change in length experience? And our change in length is what? L2 minus what? L1. Now, what was our L2? Our L2 from our calculation was 30.285 minus our L1 is 30. That will give us 0.285 cm. That will be the expansion experienced by this material. That will be the change in length of this material. So lastly, let's look at question number 3. So that's our 2A. Let's see question 3 now. Question 3. Can we look at question 3? Yes. Let's look at question 3. Calculate the expansion experienced by a material. Calculate the expansion experienced by a material. Calculate the expansion experienced by a material. Calculate the expansion experienced by a material whose initial length was found to be 40 meters. Whose initial length, that is the original length, was found to be 40 meters. Whose initial length was found to be 40 meters. Whose initial length was found to be 40 meters. When the temperature increase, that is the increase in temperature. When the temperature increase in temperature means change in temperature. When the temperature increase was found to be, or when the temperature difference, you can also put it that way. When the temperature difference was found to be 200 degrees Celsius. When temperature difference was found to be 200 degrees Celsius. In bracket you write, take alpha to be equal to 1.0 times 10 to the power minus 5 per degree Celsius. Alpha can either be, can either be given in form of per Kelvin or per degree Celsius. Any of them is possible. So what will be the answer to this question? Instead we look for the expansion experienced by the material, the initial length is 40, and the temperature difference or increase in temperature was found to be 200 degrees Celsius. So what will be the expansion experienced by that material? So remember, I told you guys that expansion, change in length is same thing as what? Alpha L1 change in theta. Alpha L1 change in theta. So how we will solve that to get our final answer? So our change in length will be equal to, what is our alpha from the question? Our alpha is 1.0 times 10 to the power minus 5 times, what is our L1 from the question? Our L1 is 40 times, what is our change in temperature? Our change in temperature is 200 degrees Celsius. So if you multiply this with your cash calculator, 1.5 exponential minus 5 times 40 times 200, you are going to have something at something like 0.08 meters. That's what I go have. 0.08 meters. That will be the expansion experienced by this material. That will be the expansion experienced by this material. Now, that will be the expansion experienced by this material. So, I can also ask you a question. Let's say question 4. From question 3 above, from this question 3 above, that's from the question 3, this is our question 3 here. From this from our question 3 above, what is the final length of the material? What is the final length of the material? Our final length, our L2, is equals to L1 bracket 1 plus alpha change in theta, or we also have that change in length is equals to L1, and that is L2 minus L1. So is either use this or use second relation. So let's use this one. This is very simple to use. And if you use that, we're going to have we already know that our L2 now will be equal to moving L1 to this side, change in length plus L1, and that will give us what is change in length? 0.08 plus what's our L1? 40. Now, let's say 40.00 so that we can add it together very well. Now, we're going to have this place 8 plus 0, we have 8, 0.0 that is 0.40. So we're going to have 40.08 in meters as our final length of this one here. The final length will be 40.80 meters. That will be the final length. You still apply this formula, you're still going to get that same thing. That's what you're still going to have. So thank you all. God bless you. I'll see you in our next class. So ensure you comment if you have any question and share this video. God bless you all.